inviting me to have this and have me talk about the emission mechanisms. All right, I'll quickly jump into the challenges that we face as the community. So FRBs are some of the largest amplitude electromagnetic waves that we know of, and that can be defined by this strength parameter A, and it's just the ratio of here you have the amplitude of the electric field of the wave, and ME is the mass of the electrons, omega is the frequency of the FRB, and it's extremely large, 10 to the 5 at a radius of about 10 to the 8 centimeters for 10 to the 42 Earth per second FRB. And some of the most powerful lasers on Earth can get to the strength parameter value A of about few or even 10 max. This means that the electrons' oscillations are so relativistic that the Lorentz factor that they experience is comparable to the electric force. The second challenge is the brightness temperatures, which can be obtained from the Rayleigh-Jeans law. Over here, and for FRBs, this happens to be about 10 to the 36 Kelvin. If an ensemble of incoherently emitting particles has some temperature T, then the brightness temperature cannot exceed that. So this puts a strong constraint on the emission mechanism that it has to be a coherent emission mechanism involving large number of particles emitting radio wavelengths in a phase. And how many particles do we need? And yeah, so that's the number of particles that you need. It's about 10 to the 26, assuming that these are electrons that are emitting. And the immediate question is, how are you going to get all these particles work in cohesion to produce FRBs? There are a few ways, and there are multiple flavors of models based on these ways to produce coherent radio emission. I will go through each one of them in this talk. Before I get into it, quick primer on different types of MHD waves. I'll be talking about this a lot. You have alpha waves where the oscillation is moving along the field lines. So this is an alpha wave, whereas there's another kind of MHD wave called the magnetosonic waves, where the compression moves even perpendicular to the magnetic field lines, across the field lines. And then I'll be using these three icons to denote whether this emission mechanism can operate in neutron stars, in jetted black holes, and whether this is also numerically simulated, whether this emission mechanism also occurs inside computers. And I will not be using this icon anywhere. All right, so charged bunches. So that's one way. You can just bunch up these charges somehow and then let them radiate in cohesion. So this is a snippet from Alex's paper, and you can see similar lines in many papers. You just consider that these bunches automatically form, and the origin of the electric field that lets these bunches travel at the speeds that's required. You just assume that it exists. So it's not really clear how these exist. And one way for them to exist is through something called two-stream instability. So this is where you have a beam of plasma going through a background different plasma with different differential speeds. So here I'm sending this green beam of electrons into a background beam denoted by the gray dots. And this is what you see happening. So this can be imagined as something that's happening along the field lines of a neutron star, for example. What you see is that as a beam starts accumulating certain fluctuations due to these two-stream instabilities, and you form really nice bunches. And these are phase space bunches that you form. This is y-axis space, and this is Vy. That's the forward velocity perpendicular to the motion. But these bunches do not seem to last for a reason that they last, and let's assume that they exist in the neutron spheres, and then we can construct some models for FRB radiation mechanism. One of such models is the curvature radiation. So this is where you have a neutron star, and these in the background field of some particles, and you form these bunches denoted by these stars. You need 10 to the 14 Gauss magnetar-like fields, and this has to happen at extremely close distances, 10 to the 7 or 10 to the 8 centimeters, for the particles to not have velocity dispersion perpendicular to the field lines and to maintain coherence. So the particles clump, and they form these clumps of the size of about FRB wavelength, about 30 centimeters, and you need these large parallel electric fields along the field lines to sustain these punches, and they have to follow some accelerating path. This can happen along closed field lines or open field lines. There are other sub-flavors of this model. And there are a few predictions. For example, broadband emission, you can expect some flavors of these models, millisecond duration fast optical bursts, and a time-dependent polarization angle swings, the rotating vector model, and so on. And the burst rate is also expected to decrease with this frequency near to the minus 2/3. Another flavor is of this that invokes bunches is called free electron laser. So you have you send a beam of electrons through oscillating magnetic fields, something like this, and a laser-like emission, laser-like coherent light. This is a very well-studied phenomenon in laboratory plasmas. And Max can invoke that in the magnetospheres of neutron stars, where the neutron star's crust oscillates, it launches these alpha waves that I talked about earlier, causes these wiggles along the field lines, and he also invokes a coherent, a relativistic beam of particles that are launched from process, say like magnetic reconnection, and when these beam of particles pass through these alpha waves, they bunch up due to what's called ponderum motive force. So this is where when you have an inhomogeneous oscillating electromagnetic field, and you put a particle in that field, the particle not just oscillates, but it also experiences a force that pushes this particle away from the high intensity of the radiation. That's the ponderum motive force. So this bunches the particles, and these bunches travel along curved field lines, and power that is emitted is comparable to the Larmor power that you can compute for coherent, for the curvature radiation that I talked about earlier. But these bunches also Compton and Raman scatter these Wigler alpha waves to produce FRB-like emission. There are a few other predictions from this model. The emission duration is about 1% of the spin period. Other interesting prediction is that if a narrowband emission comes through this mechanism, it has to have a strong linear polarization and only linear polarization. You could also expect some giant gamma ray flares with millisecond duration rise times. Another flavor that invokes bunches is through inverse Compton scattering. Again, crustal oscillations happen in magnetars, and this not only launches alpha waves, but it can also launch fast magnetosonic waves. And these fast magnetosonic waves can travel across the field lines. And again, these FMS waves can create bunches by themselves with appropriate sizes comparable to FRB wavelengths at about 10 to the 8 centimeters. And then Compton scattering happens, where these bunches, which are traveling at extremely large Lorentz factors, 10 to the 3 or 10 to the 4, it Compton up scatters the low frequency, kilohertz frequency, fast magnetosonic waves to gigahertz path. That's another model. And the predictions include a very narrow band spectra, something like what we see for repeaters. You could expect some weaker and narrower, higher harmonic components in the spectrum. And you can expect 100% linear polarization and circular polarization, depending on the angle of the observer with respect to the emission cone. Okay, so the next class of models invoke population inversion, something like what you see in lasers. And I've placed this between charge bunches and oscillating currents because you will find certain conceptual features in these population inversion models that are similar to these charge bunches and oscillating currents. Okay. Okay, there are many ways to cause a population inversion. I'll focus on one way in this slide based on shocks, and then I will discuss other ways in the upcoming slides. Let's say you have a magnetized transverse shock. That is, a shock is propagating along this x hat direction, and the magnetic field lines is perpendicular to it. That's the requirement. Say if it's along x direction, z direction could be the magnetic field lines. Particles from the upstream, they enter the shock. They gyrate coherently, and they form an unstable ring-like structure in their momentum space. X-axis shows the x momentum, y-axis shows the y momentum, and it forms a ring-like distribution, a soliton-like distribution. So this is a simulation, a particle cell simulation of such transverse magnetized shocks. You can find these soliton-like structures with a density cavity formed in these simulations, which are very interesting. And that's the reason why this mechanism operates. And how it works is that the X-mode electromagnetic waves, that is the electric field of the electromagnetic wave oscillating perpendicular to the ambient magnetic field, are generated by oscillating currents along the y direction in this trailing soliton. And then the X-mode FRB-like waves are emitted, which propagate through this density cavity, a soliton, and then it goes upstream. It goes upstream, and then it causes various instabilities, these filamentation and modulation instabilities. And these instabilities have another effect in that it induces an XBX, a magnetic field along X direction, and that gives rise to these O-mode electromagnetic waves, where the electric field is oscillating parallel to the ambient field due to the oscillating current along Z direction. The X-mode and O-mode oscillations are extremely important to explain the polarization position angles that you see from the different FRBs. This is the so-called synchrotron measured instability. By synchrotron, I typically mean that the emission is happening at very high harmonics of the particle gyro frequency, and you expect continuum spectrum. And the Maser efficiency is goes as 0.03 over magnetization. Okay, so the place where this mechanism works could be, for example, flaring black hole jet, or a magnetar, a flaring magnetar, or even merging neutron stars. The transverse magnetic shock it can propagate into either baryons or into electron-positron plasma, and that can determine the high energy counterparts that you expect from FRBs. And the emission radius is large, AU scales, to avoid the induced Compton scattering and other optical lithic regions close to the neutron star. Predictions involve a synchrotron afterglow at X-ray GeV ranges for a baryon optical band. And you expect very high, close to 100% degree of linear polarization. Both constant and swinging polarization angle is possible because, like I said before, if you only emit X-mode waves, it's going to be a constant polarization angle because the ambient field is not changing much. But if you also emit O-mode waves with a perpendicular electric field oscillation, the superimposition can give rise to changes in the polarization angle within a burst. And this can also happen at 10 to the 13 centimeters at far away distances. Yeah, and the prediction is a narrow spectral energy distribution brought on by differential Doppler shift. Another way to bring about the population inversion is by steepening of an alpha wave. So you have a magnetar that quakes, launches kilohertz alpha waves, and the wave steepens, that is, the oscillating magnetic field of the wave is now larger than the ambient background magnetic field at about 10 to the 8 centimeters. It generates closed magnetic islands called plasmoids that you see here. And these plasmoids are ejected from the magnetospheres. These are seen from force-free numerical simulations. Are ejected from the magnetospheres, and these plasmoids then accelerate and drive ultra-relativistic shock ahead, and which can harbor synchrotron measured instabilities and produces FRB at 10 to the 13 centimeters. One of the interesting predictions is that this merging chain of plasmoids that you see here could produce higher frequency, shorter duration, and fainter bursts. And if you have a pair of bursts, something like what you see in SGR 1935 from our galaxy, the prediction is that the latter one would be a bit more energetic than the former one. And the third sub-flavor invoking such population inversions invoke something called monster shocks. This is a very interesting new idea where, again, you have quaking magnetar or a neutron star collapsing into a black hole where it works. The dipole background magnetic field of a magnetar goes as 1 over r cubed, whereas the wave amplitude goes as 1 over r, the fluctuating amplitude. So the ratio goes as r squared. So the fluctuating amplitude as a normalized to the background field, it increases as you go to large radius. So it can be understood from this schematic. In a particular phase of oscillation, the wave B field and the background field are aligned, and in another phase, they are anti-aligned. So in this case, the electric field is smaller than the total magnetic field, whereas in this case, the electric field is larger than the total magnetic field. So this is a dangerous condition. So when electric field gets larger, when E squared is larger than B squared, the assumptions of ideal magnetohydrodynamics, they break down. And that's what's seen in this particle cell simulation by Arno and Amir. Black curves show BZ, red curves show oscillating EY. At some radius, EY gets larger than BZ, or E squared gets larger than B squared. That's where particles start accelerating, and it produces a very strong shock. And this is one of the strongest shocks in the universe. And you can see it forming over here. This also forms these soliton-like structures, which can harbor synchrotron measured instabilities. The very interesting thing is the synchrotron measured instability in this scenario happens at 10 to the 8 centimeters, extremely close distances from the neutron star surface. And most of the energy goes into X-rays, about 1,000 goes into gigahertz band. Another way is through non-resonant interactions with alpha waves. Magnetar quakes, produces alpha waves, and these alpha waves can interact with the magnetized and relativistic plasma in the magnetosphere that are at a higher temperature. And the reason why they have to be a non-resonant interaction is because the gyro frequency of the particles in the magnetosphere is much, much larger than the frequency of the alpha waves. That's the non-resonant condition. This is the omega c, the cyclotron frequency of the particles, and this is the alpha frequency, and this is the wave vector, and this is the speed of the particles along the field lines. What I show here are the particle distributions. You have a Maxwellian distribution of particles, and then as this interaction happens over some time, you form these crescent-like shape in the momentum phase space. This is lifting the particles to some sort of a metastable state. This is a population inversion, and this can give rise to synchrotron measure like. Some of the predictions is that this mechanism of synchrotron instability has a much larger efficiency than the shock models, depending on the plasma temperature. It could potentially expect a much higher frequency and even fainter emission from even smaller radii, smaller than 10 to the 11 centimeters. 10 to the 11 centimeters is where you expect gigahertz emission. And this has a strict limit and it cannot produce extremely low frequency FRBs below 0.few gigahertz. We haven't seen FRB 121102 below a few, below some frequency. So if maybe this could be a candidate for that. The other third mechanism is through oscillating currents. Okay, yeah. So a flavor of emission mechanism that invokes oscillating currents is called is through magnetic reconnection. This is where you bring magnetic field lines of opposite polarity next to each other, and then they snap into each other, thereby changing the topology of the field lines and giving away energy from the magnetic fields to the plasma. So this can happen in the striped jets of black hole accreting black holes, or you can also have neutron stars, of course. Magnetar crust quakes. It launches a low frequency, again kilohertz pulse away from it, and what happens is that these propagating pulse, it reaches a light cylinder and it propagates beyond the light cylinder, which is where you have these current sheets. Current sheets are the locations where you have these oppositely oriented field lines, and the region between them are regions of current. That's seen as these tails in these particles, these global peak simulations of neutron stars. So the green ones are the magnetic field lines. As you can see here, these are going out, these are going in. The current sheet is where a flip happens. And that's where magnetic reconnection also happens. And this is a triggered event where the low frequency pulse hits the current sheet and then causes the formation of what are called plasmoids, which are basically variable linear currents. And here's a movie that shows what happens during a reconnection event. So reconnection is triggered in the center, and you form these plasmoids. And these plasmoids merge into each other because currents of same direction, they attract and they merge. And these merging events perturb the magnetic field immediately surrounding these plasmoids. And these perturbations give rise to higher frequency fast magnetosonic waves propagating radially away from the merging site. I'll play this movie again because it looks good. The waves, the quasi-spherical waves that you see emanating from this region are the outgoing Poynting flux from these mechanisms. And there are a few other predictions, conversion efficiency of about 10 to the minus 3, and the emission frequency scales as luminosity of the flare to the 5/8, set by the size of the plasmoids. And the smallest plasmoid mergers could give rise to extremely narrow features of the order of tens of even hundreds of nanoseconds. And this happens at about 10 to the 11, 10 to the 12, 10 to the 10, 10 to the 11 centimeters and beyond. And you expect 100% linear polarization and the constant polarization angle from all the bursts. Another flavor of oscillating currents is something called force-free FRB. So what is force-freeness? So force-free is basically a set of closed set of equations that describe the electromagnetic field of a magnetically dominated plasma. So you just have enough charged particles to screen the electric field such that E dot B is 0 and B square is larger than E square. But the plasma is very diffuse and barely exchanges stress energy with the fields. So you can just ignore the inertia of particles. As Roger says, a tsunami doesn't care about the vibrations of water molecules. That's the approach of this force-free FRB model. So magnetar quakes launches a pulse of toroidal oscillating magnetic fields and current propagating along the open toroidal flux tube. These turbulent fluctuations steepen at about 10 to the 7 centimeters, reach FRB scales, centimeter scales, about 10 to the 9 centimeters. It mode converts to electromagnetic waves and propagate. Here's another movie. This is a turbulent system, and the bottom right panel shows the current density. This shows the gamma beta momentum, and the top right shows the Poynting flux. All the turbulence is initiated at the center of the box. You see the Poynting flux eventually going, emanating away from the box and spreading the entire domain. So that's sort of the idea. You can expect broadband polarized emission up to 10 gigahertz. Curvature GeV can be produced. Final couple of slides on that could sort of disappoint a lot of you. I'll quickly touch upon the nonlinear propagation effects that Robert did not talk about, which is that remember that the FRBs are high amplitude waves, where the A parameter is extremely larger than 1. So the electrons in the upstream medium, they gain an effective mass given by this. So if this strength parameter is 10 to the 4 or even 10 to the 5, 10 to the 6, you can have somewhat like a negatively charged protons. This actually changes the rate of induced Compton and Raman scattering, and the dispersion measure experienced with the FRBs locally changes everything. This can also change the refractive index of the medium surrounding the FRB, because the refractive index, as Robert pointed out, has a component that is plasma frequency squared. And plasma frequency is dependent on the mass of the charged particles. And if the mass of the charged particles changes by this, plasma frequency changes, and the refractive index changes. So if you have a rising pulse of an FRB, the earlier parts of an FRB could be experiencing different refractive index than the higher peak of an FRB. So it completely changes the propagation curves. And this can give rise to lots of plasma instabilities, filamentation, modulation instabilities that can imprint different temporal and spectral structures onto the FRBs that are separate from the emission mechanism. Quick movie, I'm sending an FRB like pulse through a medium, and then it completely changes the properties of the FRB as it passes through it. I'll quickly run through my conclusions here. It is possible that multiple emission mechanisms can operate within a single engine. Different flavors of population inversion or oscillating current models could operate in multiple engines, neutron star or black. And measuring the emission radius does not inform what the emission mechanism is. Recall the monster shock. It invokes synchrotron maser happening at 10 to the 8 centimeters. And the short width timescales that you observe from new FRBs does not again translate to corresponding emission radius immediately, because recall plasmoid mergers happening at 10 to the 12 centimeters. Extremely small plasmoids can merge and produce very short features and nonlinear propagation effects that can impart these extremely short duration timescales onto FRBs. It's very challenging to pinpoint one emission mechanism without understanding these nonlinear wave-particle interactions. And we need more theoretical developments supported by computational simulations to increase the predictive power of models. I'll stop here.
Thank you, Navin. That was a very informative talk. A lot of things are something that we don't think day to day. So I'm sure there are a lot of questions.
Yeah.
One second.
Yes, the catch box. Yes, so this is Robert May speaking. I just gave the last very nice talk. I wanted to wrap my head around a little bit about the current sheets, which happen just outside of the magnetosphere. So in that case, you've got reconnection just outside of the magnetosphere, and I'm trying to figure out the geometry from here. Oh, sorry, outside of the light cylinder. Yes, thank you. I'm trying to figure out from the geometry, would would it only interact or would it only reach our line of sight at specific viewing angles? So would you still see the periodicity of the source? And could it occur anywhere in the current sheet? So subsequent bursts could be separated by about a light cylinder on the sky?
Good question. So it is definitely viewing angle dependent, and I'm not sure about the periodicity here because these current sheets, although it looks like two-dimensional structures, they have some inclination angle dependence to them, and these are like tori, something like what Jans has drawn here. So they happen in all azimuthal angles pretty much. So I'm not sure if that would have an imprint of periodicity there. And there, and along the current sheet, yes, plasmoid mergers could happen anywhere, but the sizes of these plasmoids will be different, so they may not fall in the gigahertz band.
Okay.
Young Han, please.
Hey, Navin, very nice talk. I just have a follow-up question about this model. Yes, the C1. Because you need a fast magnetosonic wave to do this, compression of the current sheet. But you also mentioned the Alex Chen's paper, the fast mode may experience the E square larger than B square. So maybe this fast modes cannot escape all the way to the light cylinder. Is that right?
Sorry, you're asking if the fast modes could escape beyond the
Yeah,
light
because
cylinder?
it may, this is my question. So can this mode really propagate freely all the way to the light cylinder to do this compression?
Yeah, so I think the authors are careful in not claiming that these are the fast modes that are hitting the current sheet. They just call it a low frequency pulse, maybe because of that reason. But it could be any compressive perturbation that reaches the Y point that could launch this that could trigger the reconnection. But yeah, that's a good question.
Okay. Let me ask a more general questions. You mentioned various models. I see some models mainly produce very high linear polarization, and maybe they also show you very different spectrum bandwidths. So observationally, do you think all the circular the non-zero circular polarization FRBs have to use propagation effects, the additional propagation effects to do this?
Okay, good question on the circular polarization. So how can a circular polarization be produced? So you can have X mode wave and you can have an O mode wave and just put them 90 degrees out of phase, superimpose them, you get circular polarization, right? So if the linear polarization models that I've talked about here, if they can produce both X mode and O mode waves of comparable luminosities, then they can produce circular polarization. If they are unable to produce O mode waves along with the X mode waves, then probably propagation is the way to produce circular polarization, or they just don't work for that particular source.
Okay, thanks.
More questions?
I think so. Let's go. Let's try.
Hi, my name is Om Gupta, and I wanted to ask a question on your last slide, which is when we have a very powerful electromagnetic wave propagating through the plasma, my understanding is that the head of the wave would interact with the plasma and with the ponderomotive force move the plasma ahead,
right,
so that the rest of the wave is not impacted so much by the plasma through which it is propagated. Is this also seen in numerical simulations?
Yes.
Okay. Thank you.
I mean, the work is still undergoing. This is for a specific value of A naught and certain other nonlinearity parameters for which you see the plasma completely pushed ahead by the FRB wave. But there are other parameter combinations for which you don't see such full flowing happening, but some plasma goes in, and you see, for example, in this video that I just played, some plasma there is some accumulation happening in front of the wave, but some plasma manages to get past the head of the wave. So it's very much under exploration.
All right, let's continue the discussion. We're well into our lunch time now.
Thank you.
Let's thank the speaker again. Thank you, Navin.